Hi everyone. The last 120, 130 years have been the most revolutionary years in science. There have been so many amazing discoveries that it's difficult to choose which one is the most important one. So if somebody had to ask me which is the most important discovery that has changed our life completely, I would say without any hesitation, quantum mechanics. It's a discovery of how really the electrons and other subatomic particles behave at the level of the atom. Because quantum mechanics has impacted our lives so much that it's actually unrecognizable. And we'll talk about today how it came about and what kind of applications and revolutions it has led in our lives. At the beginning of the 20th century, 120 years ago, there were a number of phenomena in physics that could not be explained with classical physics. We could not understand a number of phenomena, especially a phenomenon that have to do with light. And I'll show you one interesting phenomenon with some, we're going to set fire to some metallic ions, and I'll show you what happens there and how the classical physics could not explain that. So the first thing we do, it's just a nice little example. I'll put some alcohol as in order to make a fire, as a fuel. I'll start the fire, there it is. It's a small fire. And now I'm going to put a little bit of powder. This is a lithium sulfate powder. And I'll sprinkle it on the fire and watch what happens. The fire turns red, a pinkish with a slight blue tinge, but it's red. It's incredible. When people were doing these experiments in the 19th century, they just couldn't explain them. How is it possible that one fire that is a normal color, what is a little bit yellow, a little bit orange from the atmosphere, turns red? If I now, instead of lithium, I add a little bit of sodium, it turns a very bright yellow, orange. So it's a different metal ion gives a different color. So that means the color that we see there, which is the photons from the color, from the light, are different color. And if I add copper, this one is a copper chloride, so copper ions, watch how beautiful it turns. A fantastic blue, bright blue color. Now, this type of observations were done in the 19th century, but there was no ways of classical physics to explain them. And that's why this and many other observations led physicists at the turn of the 20th century, at the beginning of the 20th century, to try to explain them. And that was the main revolution. At that time, Max Planck first, and then other people, Niels Bohr, even Einstein, and many other theoreticians, Max Planck especially, postulated that in order to explain this, the electrons around the atoms cannot be in any energy level they want. They cannot have any energy value they want. There have to be very specific energy levels, because what happens is by giving the metallic ions energy, we displace the electrons on the outer shell to a higher energy level. That's what the postulation was, that there were different energy levels. And no subatomic particle was allowed to be between those energy levels. They couldn't have any other energy except at those levels. So by giving energy, you push one of the energy of the electron to a higher energy level. We call it excited atom. And then immediately that jumps down to the lower energy level and releases the difference in energy. And that difference in energy comes out as a photon of very particular wavelength. Because the wavelength of the photons of the light, Einstein told us that the photons have different energy according to the light. And the light is the manifestation of the energy level. And that's the explanation. This type of experiment and other phenomena could only be explained with quantum mechanics. And it's a beautiful demonstration, and the copper is still burning, you can see it's still blue, and it's a beautiful demonstration, but can only be explained with quantum mechanics. So this was now the beginning of quantum mechanics. But then many other things came up. The theoreticians started looking at it, and they realized it's not only the energy levels, but there's also other very complicated, very unusual ideas about quantum mechanics. For example, that the position of the electrons is probabilistic. You can never say the electron position and speed is specific. These are different consequences of quantum mechanics, but we'll concentrate on the energy levels. And concentrating on the energy levels, years later, decades later, it was possible to start the revolution, the electronics revolution, which of course led to the computer revolution. What happens is that they noticed that some metals, the energy levels of some metals could be adjusted. You could adjust the energy levels, especially the gap, what we call the energy gap between energy levels, adjusting it by doping the material with some other elements. So starting, the most important material, of course, is silicon, and there is a silicon wafer. This wafer comes from a huge block, a single crystal cylinder. Usually they are a meter long, and they're cut into very, very fine slices. This is called a wafer. This other side is like a mirror. This side here, by a technique called, a chemical technique, it's possible to print integrated circuits. Integrated circuits contain millions and billions of elements. Could be transistors, could be different elements. So lithography allows us, and to this day we still use the same way, allows us to print on this material different layers with slightly different silicon doped with other atoms. So that was the beginning. From these hundreds of different integrated circuits, each one of those is put into one of these integrated circuits, and we have, of course, electronics, the integrated circuit electronics. This is a beautiful one. It's actually a CPU, a central processing unit, from an old computer. That's all it is. In fact, it's the center of this chip. This is the chip that comes from there, and on this side is hundreds of connections. And of course, nowadays, these microcomputers, microprocessors are everywhere. This is a processor that we use for signal processing, connects to a computer via USB, etc. And of course, memories, chips are the same. Each one of those contains millions or billions of transistors, and each transistor, each element is actually a memory. Okay, and of course, the capability of making these integrated circuits allowed us to have the revolution, the computer revolution, which of course led to the internet revolution. Because computers allowed programming, and programming allowed for us to, in order to have programming, you had to have a computer. And so at the moment, there's an incredible level, incredible quality of programming and computers. And of course, recently you could have the different programs on smartphones. All these things became possible because of the quantum mechanics, the applications on silicon, etc. We wouldn't be able to do what we're doing now, this video, without the quantum mechanics, understanding of quantum mechanics. That was a major revolution, and of course it's everywhere in our lives. Everywhere in our lives completely. But another revolution is the development of lasers. Lasers, there it is, there's a green laser, and this one is a red laser, which is a lower energy than the green, and there's other blue lasers which are even higher energy than the green, etc. So lasers are what they're called. The laser comes from light amplification by stimulated emission of radiation. It means that we give some energy to the electrons. The energy allows electrons to go to a higher energy level. They drop down, and the difference in energy again between the energy levels gives us this particular color. So this one is from a different material, and this one is could be ruby, not ruby. Sorry, it's helium. This is helium, etc. Different gases or crystals, etc. So this is a laser, and with lasers we're able to send data a huge distance at an incredible high speed. And we do this with the optical fibers. And look at this, I'm going to send, look at the tip of the fiber, the one that's pointing towards you. You can see there is the laser that is sending information through this fiber, and of course these fiber optics, they connect all countries in the world nowadays and gives us internet and communications and everything. So laser is a second major application. Another huge application is atomic clocks. I'm not going to go into the detail, it's just the atomic clocks use crystals like cesium, and knowing the number of transitions between higher and lower energy levels, which are billions per second, then we're able to make a clock, to have extremely accurate clocks, which enable, if we put a clock on a satellite and a clock on the Earth, enable GPS. The global positioning system is done by quantum mechanics, by making atomic clocks on satellites and on the Earth. So that's a major application for ships, for airplanes, for cars, for ourselves, etc. A fourth major application is in medicine. Medicine, you've all heard of MRI scanning. It's actually the correct name is nuclear magnetic resonance imaging, MRI. And what it does is that by looking at the state of the hydrogen atom, it's a quantum mechanical state, that we're able to detect if there's any anomalies within the body. If the hydrogen if there's some damage, some cancer or inflammation or something like that, and we're able to see it at a very high resolution inside the body, MRI. These are four, and together with the informatics, programming, 5 major applications that we cannot live without. Our lives have changed completely. Nobody could even dream 100 years ago our life would be like that now. But then these are artificial applications. The humans have made them. They're inventions based on the discovery. What happens in nature? Well, nature uses quantum mechanics every moment of the day. There's a lot of very good evidence that it uses quantum mechanics in our bodies, in nature. But the 2 major applications without which life could not exist, the first one is fusion in the sun. Without quantum mechanics and a phenomenon called tunneling, don't worry about the details, quantum tunneling, the fusion would never start in the sun. There was not enough energy, enough temperature and pressure in the middle of the sun to be able to start the joining, the bringing together of 2 hydrogen atoms to make a helium. The beginning of fusion. And yet it happens, and it happens because of the tunneling effect. Without quantum mechanics, there would never be life on Earth. And another natural phenomenon is radioactivity. Radioactivity and also the fission or the splitting of atoms to create energy. The splitting, as you know, the 2 remaining atoms after splitting have lower mass, and the difference in mass, because of Einstein's famous equation of energy mass, the difference in mass comes out as energy, and you can have atomic bombs, of course, but you can also have a peaceful means of producing energy and electricity. So these are the 2, and as I said earlier, there's good evidence now that quantum mechanics plays a major role in consciousness, in the operation of the brain, and other operations within the body. So with this, I want to leave you with this final conclusion that quantum mechanics and the operation and the way that the atoms work, the subatomic particles, would not, if they didn't have the way they work in quantum mechanically, there wouldn't be any life. And of course, we wouldn't be none of those things that we depend on in life. So until next time, goodbye.